Well, it's great to have our last speaker before the break be Alexander Perry from University of Michigan, who will speak about Serre functors for semi-orthogonal components.
Okay, yeah, thanks a lot for the invitation. And I don't remember if this seminar is planning to continue in the fall, but in case it's not, big thanks to the organizers for putting it together the last 6 months. Okay, and I'm going to share a link right now, which is for my for the notes for my talk. So if you click on that, you might have to refresh. You have to refresh it each time you look at it, but you'll be able to go like backwards in my notes if you want to, if you follow that link. Okay, so I'm going to be talking today about some work with Sasha Kuznetsov about Serif functors of certain semi-orthogonal components. So let me just start with some motivation. Maybe I should just say in the beginning, I'll work over the complex numbers throughout my talk. That's not really necessary, but let's just do it. Okay, and just for motivation, let me give you an example of the kind of things we'll be considering. So X inside of Pn, let's say, is a Fano complete intersection of type D1, D2, up through dk. So it's an intersection of hypersurfaces of those degrees. So if you have a complete intersection like that, there's a nice decomposition of its derived category, and it looks as follows. So d of x, by the way, in this talk, d of x will always mean the derived category of perfect complexes. You can pretty much always think about the case of smooth varieties in my talk, and in that case, it's just dbco. So there's a nice decomposition of this category, which looks as follows. So there are a bunch of line bundles. So it's the structure sheaf and its twists. And there are index many of these twists. So here, ind of x is the Fano index, so it's the following positive number. So it's n plus 1 minus the sum of these di. And then, so there are these line bundles in the decomposition, and then there's this interesting piece, which is the orthogonal to those, which I'll denote by Rx. And so explicitly, this thing is just the full subcategory of all objects in d of x, which receive no x from any of those objects on the right. So this is for I bigger than or equal to 0 and less than or equal to the index minus 1. Okay, so this category here, Rx, is sort of like the interesting part of the derived category. It's the stuff that doesn't come from the ambient projective space. And in this talk, I'm going to call this the residual category. Of X. Okay, this thing is also often known as the Kuznetsov component. So AKA the Kuznetsov component of X. But since this is work with Sasha, I'm going to follow his wishes, and I'll call it the residual category. Okay, so this is sort of a typical example of the kind of category we'll be interested in this talk. And let me just give you a little bit of motivation for why you might care about these categories. So interest in residual categories. So recently people have studied these for a couple different reasons, and I'll list two of them. So the first one is that there are a lot of relations, often conjectural, to birational geometry. Okay, and I'll just mention, in case you haven't seen it before, the most famous example of this kind of relation is this conjecture by Sasha, which says that if you look at X above, which is just a hypersurface of degree 3 in P5, let's say a smooth one, So I'll call such a thing a cubic fourfold. Well, there's this big open question about whether such things are rational. And the conjecture is that X is rational if and only if this residual category is equivalent to the derived category of a K3 surface. Okay, so I think that's a conjecture which has motivated a lot of work. I won't really say anything else about it in this talk, but that's sort of, these kind of relations are one of the motivations for studying residual categories. So that's the first, maybe one first reason why you might be interested in these. And the second reason is that moduli spaces of Bridgeland stable objects in these categories. So my notation for such a moduli space will be M sigma RXV. Okay, so I'm not going to say a lot about Bridgeland stability in this talk, but it's just some notion that allows you to form reasonable moduli spaces of objects in a category. So this space depends on a stability condition and a choice of a numerical invariant. And these moduli spaces have a lot of rich structure when you consider them inside of these residual categories. So let me just mention like two examples of that. So for instance, in some work with some of the people here, so Bayer, Lahoz, McCree, Newer, and Stellari, we showed the following. So if X is a cubic fourfold, as above, then these moduli spaces are actually hyperkähler varieties. So they're hyperkähler, and we showed that they're like non-empty. They actually have the expected dimension. There's some formula for the expected dimension and it's the actual dimension. So they're hyperkähler of expected dimension. Okay, and that sort of unified a lot of previous constructions of hyperkähler varieties. So that's maybe one interesting example of a moduli space. And I'll just mention one other result about these spaces. So this is a result by Pertuzzi and Yang. And what it says, so, okay, so these categories have been studied for many other Fano varieties. So for instance, for Fano threefolds. And let me just give you an example. So if you take X to be a cubic threefold, then what they showed is that these moduli spaces are smooth. So they're actually some natural smooth varieties that you can attach to any cubic threefold. And yeah, so those categories have been useful for applications too. Like, using these moduli spaces, for instance, you can like reprove Torelli theorem, the Torelli theorem for cubics. And there's been a lot of work in that direction by studying residual categories for Fano threefolds. So this is like some brief summary of why you might care about these categories. And yeah, I think in general, there should be a lot of other potential applications of these categories in algebraic geometry. Is there any questions before I keep going? That was like the motivation.
Can I ask a question? So in this cubic threefold case, can one describe this Rx better? Can
you describe? I don't think that there's a sort of super concrete description of it. No.
But for special cases, this you can.
It's never equivalent to the derived. For instance, it's never equivalent to the derived category of a variety. If you look at singular ones, it's close to the derived category of a curve. But yeah, for smooth ones, it's never D of a variety if that's what you're looking for.
Okay, thanks.
Sure. Any other questions?
Sorry, I may have missed this.
5/3.
What was that?
Its dimension is 5/3.
Right, that's true. Yeah, it's Serre Functor to the 5th power is a shift by 3. Yeah, that.
Okay, maybe one more question. What about cubic fivefolds? Can one say? I mean, can you kind of extend this list and get some?
Yeah, I'll mention cubic fivefolds towards
the end. Cubic sevenfolds.
Yeah, they're all pretty interesting.
see.
I'll
Thanks.
mention cubic fivefolds later in the talk, maybe. But not so much is known about moduli spaces in those cases because we don't have stability conditions. So in general, it's not known that stability conditions exist. But yeah, I'll mention something about those later. Was there any other questions or?
I may have missed this, but what is the y or v in the moduli space object?
Okay, I didn't explain that really. It's an element in the K theory.
I see. Okay, thank
It's
you.
some numerical class for the objects that you consider. Okay, cool. So yeah, so our goal is to understand these residual categories, and what I want to talk about today is sort of one of the most basic invariants of these categories, which is the Serre functor. So let me just remind you what the definition is of a Serre functor. Okay, and this is related to Sasha's comment about 5/3, but I'll get to that later. So here's the definition. A Serre functor of a triangulated category. Oops, I don't know what happened there. Of a triangulated category C is an autoequivalence, which I'll denote S sub C, that satisfies the following property. So Homs from E into F should be functorially isomorphic to Homs from F into the Serre functor applied to E dual. So this is for any objects E into F in your category C. Okay, and just in case you haven't seen this definition before of a Serre functor, let me just give you an example. If X is a smooth proper variety, I guess even Gorenstein is enough, but if you have a smooth proper variety, then the Serre functor is given by tensoring with the canonical bundle shifted by the dimension of your variety. So yeah, so in general, you should think of a Serre functor as like an analog of the dualizing complex of a variety. And you know, from that point of view, it's sort of one of the most fundamental invariants of your category. And maybe I can mention that actually an understanding of this Serre functor plays an important role in these applications I mentioned before. And in those cases, what's used is a result of Sasha Kuznetsov, which tells you about the behavior of this Serre functor in the case of a hypersurface, so where the codimension is just 1. And what I want to talk about today is a generalization of his result, which in particular applies to any Fano-complete intersection. So that's sort of the goal, to tell you about Serre functors of residual categories in general. Okay, and actually I'm going to try to state the main result in just a second. I just need one other piece of notation. So the result is going to be in terms of something called spherical functors. So let me just remind you of the definition of those. So let's say that psi from C to D is some functor of triangulated categories. And let me assume that this functor admits a right adjoint. And I'll denote the right adjoint by psi shriek. So psi shriek from D to C is a right adjoint. Okay, so in this setting, you can define twist functors. I'll call them T psi shriek psi. So this one is an endofunctor of C, and T psi shriek, which is an endofunctor of D. And these things are defined by, distinguished triangles of functors that look as follows. So you take the unit of the adjunction, and you take the fiber of that. So that defines what I'm calling T psi shriek psi. And similarly, you take the co-unit of the adjunction. Okay, and you take the cone of that, and that defines what I called T psi shriek. Okay, and technically to make sense of these cones and this fiber, you need to work in an enhanced situation. So I'm sort of suppressing that here. These are really enhanced categories. Like, for instance, any residual category has an enhancement, so it makes sense to form these cones here. Okay, so whenever you have a functor with an adjoint, you can define these things that I call the twists. And we say that psi is spherical if these two twist functors are actually autoequivalences of your category. Okay, and this notion of a spherical functor is actually a pretty powerful way of constructing autoequivalences of categories in general, and they've been studied quite a lot. Let me just give you one example, which is kind of relevant for this talk. I'm not even sure how relevant it is, but here's like an example which is at least related to what I'm going to say. So let's say that, well, it is related. Okay, so anyway, so say that I have I, which is the inclusion of a divisor x into m. This is a divisor. Then you can look at the pullback functor from the derived category of m to the derived category of x. And this pullback functor is spherical. Okay, and if you want, you can, maybe as an exercise, you can check for yourself that explicitly these twist functors in this case are given as follows. So tensoring on m with minus x, and then the other twist is given by tensoring on x with minus x shifted by 2. Okay, so that's just the computation you do, and clearly those are autoequivalences, so this is a spherical functor. Okay, so now I think I can state the main theorem actually, which gives a formula for the Serre functors of residual categories. Let's see. Maybe I should start on a new page. Okay, any questions about this page before I keep going? Okay, yeah, let me start on a new page just so I have room. So here's the main theorem that we prove. So first, let me tell you the setup. So I'll assume that we're in the following situation. M will be a smooth proper variety. And again, Gorenstein is enough, but let's say smooth and proper of some dimension, which I'll call n. Okay, next I want to assume that the canonical bundle of M can be written as O of minus little m for some line bundle O of 1 on M. And here little m is some integer greater than or equal to 1. Okay, and then further I want to assume that the derived category of n has a semiorthogonal decomposition of the following form. So there will be a bunch of copies of a category that I'll call B or Bm. So there's Bm twisted by 1, all the way up to Bm twisted by m minus 1. And here my notation is the following. So like, it's what you think. So Bm twisted by 1 just means you take Bm and you look at its image under the autoequivalence given by tensoring with O of 1. So we have like m copies of this category B, and then there will be one other piece which I'll call Rm, and I'll also call that the residual category. So assume you have a decomposition like this, and the canonical bundle is O of minus m. And then finally, I'm going to take x inside of m to be a divisor of degree d. So it's a divisor in this linear system. For some integer d between 1 and m minus 1. Okay? And so what's the case that you should keep in mind? Like, for instance, if M could be a complete intersection in a projective space, and in that case, a Fano-complete intersection in projective space, in that case, this would be just generated by the structure sheaf. And X here would again be a hypersurface section of that of degree D, which by my assumption here will again be a Fano-complete intersection. So that's like a special case of our setup, the case of M, a Fano-complete intersection, and then further a hypersurface section of that, which is Fano. Okay, and so that's the setup, and the conclusion is the following. I don't know why it keeps doing that. Whoops. Okay, so there would be a couple parts in the conclusion here. So the first one is that the pullback functor from D of M to D of X is fully faithful on this category Bm. So it embeds Bm into D of X. The second part is that there's a decomposition for D of X that looks as follows. So there are a bunch of copies of the image of Bm. So I'll denote by Bx the image of Bm. So there's, instead of M, there's M minus D. So you lose a couple copies. So there's Bx twisted by 1, all the way up to Bx twisted by M minus D minus 1. And then there's an interesting piece, which again, I'll call the residual component, Rx. So again, like when X was a Fano-complete intersection, this is just the decomposition I told you in the beginning. Yeah, and the first two parts of the theorem are not so hard. They're sort of just a computation. But then the main parts are 3 and 4. So 3 says that this functor I pullback, which remember by our example was spherical. So that functor actually restricts to a spherical functor between the residual categories. So this restricts to a spherical functor, which I'll call psi, from Rm to Rx. So what I mean is that it takes Rm into Rx, and if you consider that restricted functor, that thing itself is spherical. That's not automatic from the fact that I pullback is spherical. But yeah, so that's part of the theorem, that that thing is spherical, this restricted functor. And then finally, maybe this is really the main part. If I define C to be the GCD of D and M, so the degree and sort of the index of the variety M, then we have the following formulas for the Serre functors. So the Serre functor of Rm raised to the power D divided by C is isomorphic to this spherical twist raised to an appropriate power. So it turns out to be M divided by C, composed with the shift. Okay, and then a similar thing for Rx. So let me make sure I get it right. So this is isomorphic to T psi shriek raised to the M minus D divided by C, composed with a shift. And in this case, the shift is D times N plus 1 minus 2M divided by C. Okay, so there are a lot of numerics here, but let me sort of say in words what the situation is. We start with this variety M with a nice semi-orthogonal decomposition. If you take a divisor inside of it, then there's an induced semi-orthogonal decomposition, which has this interesting residual component. This pullback functor from D of M to D of X gives you a spherical functor between the residual components. And the Serre functors of these residual components, they're almost fractional Calabi-Yau, but they're not quite. So a power of them is equal to a shift composed with the power of a spherical twist. And you know, the exact numbers that appear here aren't so important. Maybe the conceptual thing to take away is that a power is a power of the Serre functor is a shift up to an explicit power of a spherical twist. Any questions about the statement? I'll try to unpack this. Most of the talk will be sort of unpacking this and some of its consequences. Any questions about the statement though?
May I ask a question?
Yep.
It seems that the Serre functor of Rm should not depend on x, right? So yeah. So there is that true that this twist functor, this t, is independent of this x?
No, that's not true. I think. I mean, well, okay. I don't think that that's true, and it's sort of a funny thing that happens. Well, I mean, what is true, right, is if you compose this with this shift, you'll always get the same functor, right? So the power of that functor is always the same. I'm not sure that the functor itself is always the same for any given x, and in fact, I think it might not be. But that is a funny consequence of what I'm saying, right? Like if x was a phono-complete intersection and you represent it as a hypersurface section of something one dimension bigger, then for each representation of that form, I'm getting an expression for this Serre functor, right? Yeah. And this functor does depend on that presentation that you choose in general. So yeah, and I'll come back to that sort of point. Will come up again later. Okay, great. Thanks. Thanks. Yeah, that was a good question. Any other questions? Okay, well, let me make a couple remarks about the theorem, and then I'll try to tell you about some applications. So remark. So first of all, let me just mention that there exists a more general categorical, let's say categorical version of the theorem. Okay, so roughly speaking, the categorical version replaces d of m just with some category, d of x with some category, and I pullback is replaced with a spherical functor. And then you have to impose some conditions. And so with an appropriate setup, actually a version of this theorem sort of holds categorically. And maybe just concretely, I'll say that this applies to other situations. So concretely, there's a similar result if instead of a divisor, you consider a double cover x of m. Okay, so there are sort of variants of this result, but I'll just focus on the one that I wrote down today. So second part of the remark is that if you consider the special case where R of m is equal to 0, okay, right? So like, for instance, if m was projective space, then R of m would be equal to 0 here. So if you're in that kind of case where R of m is equal to 0, then what happens? So this formula is not really interesting, right? This category is 0. So this is the interesting formula. And when R of m is 0, this spherical twist is just the identity. If you just look at the definition of the spherical twist, you'll see that this is the identity. So when R of m is 0, we're getting that this category Rx is fractional Clobial. So a power of it is a shift. So let me just write down what I said. So in this case, this thing is equal to the identity. And this case here recovers Kuznetsov's fractional Calabi-Yau results. So those are the results I mentioned earlier, which for instance apply to hypersurfaces inside of projective space. So that's this is a generalization of that result. And the case where R of m is not equal to 0 is really crucial if you want to understand higher codimension complete intersections in projective space. Okay, and then the final remark is that, so as I've been telling you, right, you can keep in mind the example where M is a complete intersection in projective space, but there are other examples. So maybe I'll just briefly mention that examples of suitable M that you can take. So they include complete intersections in projective space, which I've been saying, inside of, for instance, weighted projective space, or you could take complete intersections in a Grassmannian GER Kn. So all of those varieties have sort of decompositions that satisfy these assumptions here. Okay. So that's the statement of the main result. I'm not going to say so much about the proof, which is kind of technical, but the rest of the talk will be telling you about some applications of the result. Okay, last chance to ask about the statement if there's any. Well, not the last chance, but okay, I'm gonna.
But the proof is some sort of induction argument, or can you at least comment on the proof?
I don't think I can say something too succinct about the proof. I mean, in general, right, there's some formula for the Serre functor for the, let's say the inverse Serre functor of this category is equal to the inverse Serre functor of this category composed with left mutation through these. And so if you write down that formula, what you end up needing to study is something that's called a rotation functor. So there's an auto equivalence of this category where you tensor by O of 1, and then you left mutate through here. And somehow, ultimately, the theorem boils down to studying powers of this functor via that expression I told you for the Serre functor of Rx in terms of the Serre functor of this. But yeah, it's kind of intricate. There is some inductions involved, I guess, somewhere along the way. But yeah, I don't think I can say anything that's going to be too illuminating besides that, though.
May I ask a question?
Sure.
So, is that true? Is that in this case, learn the twist and co-twist functor will be given by the rotation functors?
What was that again?
I mean, is the twist functor in this case just given by the rotation functors?
I think it's closely related. There might be like a shift or something. It might be off a little bit by that, yeah.
I see. Thanks.
But I mean, in general, how explicit can you make these rotation functors? If you take a complete intersection in some Grossmanian or so.
I'm not sure what to say about that besides the, yeah, I don't know if I can say something super explicit besides the definition that I said. I mean, it's true, right? When this category is something simpler, it becomes simpler. Like if it's generated by exceptional objects, then you can kind of simplify.
Sorry, I meant the twist functor that appears in your result.
I see. Yeah, I don't know if I can say anything super explicit about that. Yeah. Okay. Okay, so let me tell you about some applications in the second half of the talk. So applications. Oops. So I'm going to tell you, well, depending on time, sort of two different classes of applications. So the first one that I'll tell you about is related to dimensions of these residual categories. Okay, so first let me actually tell you about the definition, what I mean by the dimension of a category, which I think is kind of an interesting notion. So this is a definition due to Elegin and Luntz, and it's the following. So the setup is going to be that C is a triangulated category with a generator G. Okay, so by generator I mean a thick generator. So under cones and shifts and direct summands, it generates the whole triangulated category. That's a very mild assumption. For instance, any semiorthogonal component of a variety has a generator. So okay, so fix a category with a generator, and let's let F be an autoequivalence of the category C. So actually, I'm going to define the dimension of any autoequivalence. So the upper and lower F dimensions are the following. So there actually be two dimensions associated to any autoequivalence. So let me write down the formula. So the upper dimension is defined as follows. So it's a lim sup of the following expression. So you look at X between the generator and powers of your functor applied to the generator. Okay, and you look at the X which are non-zero, you take the smallest one, okay, you take negative of it, and then you divide by M, and you take the limit as M goes to infinity. So that's the definition of what's called the upper F dimension. And the lower F dimension is defined similarly. So it's a lim inf of the following thing. So instead of taking the smallest of those I for which the x is non-zero, now you take the maximum. Okay, and you divide by n and you take the limit. So I'm going to tell you some property. This definition might look a little bit funny at first, but I'll tell you some properties in a second to tell you that it's actually kind of a nicely behaved notion. But first, let me also say that in particular, if C has a Serre functor, S of C, then we can define the notion of Serre dimensions, which is sort of a canonical notion of dimension of your category, which I'll denote as follows. So they're just the upper and lower dimensions of the Serre functor. Okay. So the upshot, right, is that for any like semi-orthogonal component of a smooth projective variety, let's say, those things have generators, they have Serre functors, and you get this canonical notion of an upper and lower Serre dimension for such a thing. And so, yeah, let me just tell you a couple properties of this definition, which hopefully will convince you that it's kind of well behaved, at least in some ways. So some properties that Elegant and Luntz proved are that, first of all, this is well defined. So that's maybe the first thing you should ask yourself. This is indeed well defined. It doesn't depend on G. So it's independent, so i.e. independent of this choice of generator G. So second of all, as you might have guessed from the terminology, this lower F dimension is always less than or equal to the upper F dimension. So the third is a comparison to usual dimension in the geometric case. So if X is a smooth proper variety, then the upper Serre dimension is equal to the lower Serre dimension, and both of these things are equal to just the usual dimension of X. Okay, so this notion sort of recovers the usual dimension in the geometric case. Let's see. Okay, so the fourth property is that if C is a smooth proper category. Okay, let me not define smooth and proper category, but for instance, a semi-orthogonal component of a smooth proper variety, then the following is true. So then these numbers, the lower and the upper F dimension, they're both finite, so they're actually in R. I guess I didn't say that, right? A priori, these things could be in R union plus or minus infinity. But okay, if your category is smooth and proper, then actually these lim sups and lim infs are just limits, and they exist and they're finite. So it's sort of it's well behaved in that sense, this notion of dimension. And then the fifth property that I wanted to mention is that in the fractional Calabi-Yau case, so if your category has Serre functor whose pth power, let's say, is a shift by q, okay, here I think I need to say p bigger than 0. So suppose some positive power of your category is shift by q, then this implies that the Serre dimension of C, the upper and lower one, are both equal. And they're just equal to q divided by p. Okay, so these are some properties. You know, it might be, if you haven't seen this before, it could be fun to think about why they're true. I think most of these actually are followed without too much work from the definition. But yeah, so the upshot is that for any semi-orthogonal component of, let's say, a smooth proper variety, there's this kind of nice notion of dimension, namely the Serre dimension, well, the upper and lower one, and you could compute it for any variety. So here, that's what this theorem is about that I'll say now. So the theorem that we proved gives an explicit formula for this dimension for Fano complete intersections for the residual categories. So if X and Pn is a Fano, is a smooth Fano complete intersection of type D1 through dk. And let me assume all of these degrees are bigger than 1, right? If they're equal to 1, then it's sort of, then you're just in some smaller projective space. So you may as well assume they're all bigger than 1. Then there's this following formula for the Serre dimensions of the residual categories. So let me write down the formula. So dimension of X minus 2 times the index divided by D max. And the lower dimension is equal to the dimension of X minus 2 times the index divided by D min. Okay, so D max and D min are the maximal minimal degrees among D1 through dk. The index, remember, is just n plus 1 minus the sum of the degrees, which is some positive number. And so there's this very explicit formula for the Serre dimensions. So maybe I can just make a remark. So part of the inspiration for proving this theorem is that it was actually conjectured by Katzarkov and Kontsevich in their study of rationality problems. Okay, so more precisely, they actually conjectured something which was a little bit too strong. They actually conjectured that these two numbers are equal to each other, and they're both equal to this first expression here. But it turns out that's not quite true, but sort of something very close is true. You have these two formulas for the upper and lower Serre dimension, which are in general not equal. Yeah, so I think, yeah, so one of the motivations was this conjecture. I think it's kind of interesting because in general, it's pretty hard to compute these Serre dimensions. And in a minute, I'll mention an application of this theorem, but first I wanted to just sort of really briefly sketch the idea of the proof. So here's the idea of the proof. So let's say that we write our X as M intersected with Y, where M is a complete intersection of type D1 through dk minus 1, and Y is a hypersurface of degree dk. Okay, so if you unwind what the main theorem says, you have to just look at the numerics. So what it ends up saying is the following. It says that their Serif Functor of Rm to some power is, okay, let me just write it down. So I'm just replacing all of the numerics in the theorem with our specific setup. I made a typo, sorry. This is index of M. Okay, so index of X divided by C. Okay, and here C is the GCD of dk and the index of M. Okay, so the reason I wrote this down is it maybe gives you some hint as to where these numbers are coming from up here. Right, so imagine that, let's just imagine for a second that this functor was the identity, right? Then this would be saying that this category is fractional Calabi-Yau of dimension this divided by this, right? And if you just divide those numbers, you get exactly this expression with dk here. So the way you can think of this is that for each presentation of X as an intersection like this, you get a formula for the Serre functor which says that Rx is not fractional Clobial, but it's sort of off from being fractional Clobial exactly by this autoequivalence. And the statement of the theorem is that the minimum and maximum fractions that you get in that way are exactly the upper and the lower Serre dimension. And to actually prove it, you do an induction, of course. I guess that's kind of the way you might try to prove it. So let me just really briefly say. Okay, so that was supposed to explain to you sort of where intuitively those numbers are coming from. But if you really want to prove the theorem, you just do it by induction on the codimension of your complete intersection. So if the codimension is 1, then it's just a hypersurface in projective space. And as I mentioned, in that case, your category is fractional Calabi-Yau, right? That was Sasha's result that he proved a while ago. So in that case, the theorem holds. Remember, there was this property I wrote down. For a fractional Calabi-Yau category, the Serre dimensions are just given by that fraction. So in the codimension 1 case, you're good, and that's the base case of the induction. And when k is bigger than 1, so you do an induction, and what you use is some relations between the dimensions of spherical twists on the source and target of a spherical functor. So I'm not going to say much here. So you use some general inequalities that relate the dimensions of the spherical twist t psi shriek psi and t psi shriek. Right, so if you're going by induction, we can assume we sort of know everything that happens in this case, and that will give you a formula for the dimension of this autoequivalence. And so to understand the Serre dimension of this category, you sort of reduce to understanding the dimension of this autoequivalence. And I'm saying there are some general relations between those two dimensions, between the dimension of this and the dimension of this, which I'm not going to write down explicitly. They're a little bit complicated, those relations. But maybe the one thing I will say is that these general relations, they require some hypotheses to apply them. And in particular, what we need to check along the way, so these inequalities rely on some non-triviality, I'll call it, non-triviality results for the functors psi and psi shriek. So more precisely, what we end up needing to prove to apply these sort of general results relating the dimensions of spherical twists is that the functor psi is actually conservative, so its kernel is 0. And the functor psi shriek, it turns out it has non-zero kernel, but it is not 0 everywhere. So it's not equal to Rx. Okay, and so you can think of this as, this is some kind of non-triviality statement about these functors psi and psi shriek. Psi is like conservative, so it doesn't kill anything. And the adjoint does kill something, but it does not kill everything. So somehow these are sort of two of the main ingredients in applying these general results here. And I mentioned them because this, in particular, these inclusions will come back in like 10 minutes. That's why I mentioned them here. But that's, okay, so that's the very brief sketch of the proof of this theorem. Are there any questions about that?
So can I ask a question?
Yeah.
So it seems that, so does your theorem hold for this weighted projective space?
Which theorem? This theorem here?
I mean, this, yes. For example, X is like Y1, is a degree 1. This index 2 final threefold in the some weighted projective spaces. Is your theorem hold?
Well, yeah. So in that case, right, then it's actually fractional Clobial, the category.
Yeah. Okay.
And so then it's sort of, I would say, sort of by an easy argument, the Serre dimension is just the fraction.
Okay.
Yeah. Yeah, but you can run this more generally for complete intersections in like those other spaces that I mentioned earlier. Yeah. Okay, cool.
So when d min and d max are equal, is it fractional Calabi-Yau?
When d min and d max are equal, I don't think that's a good question. I don't think that's obvious. I think that's I'm not sure if that's true actually. It doesn't, I don't think it follows from okay, I'd have to check, or maybe Sasha knows, but actually I'm not 100% sure.
That's
If that's true.
definitely not true. For instance, you can take a complete intersection of
quadrants.
two
Two
quadrics.
quadrants. Yeah, you're right. You're right. Yeah. That's not true. Yeah, if you do two quadrants, you'll see it.
Yeah, in this case, in appropriate parity of dimension, this is just a hyperelliptic curve of some genus.
Right. Yeah. Good point. Sorry. Yeah. Any other questions? Okay. So let me tell you about one application of this theorem. I'll just mention this one briefly. So yeah, I think on its own, it's kind of interesting, this computation of the dimension, but it has some concrete application to stability conditions, which is actually pointed out to us by Arend and Emanuela. So what it says is that in this case where not all of the degrees are equal, so d max is bigger than d min, then there does not exist a Serre invariant, stability condition on Rx. So just, I'm not going to say a lot about this, but just to tell you what that means. So i.e., there is no fixed point for the following action. Okay, so you can consider the space of stability conditions on your category. That always has a natural sort of reparameterization action by the group GL2 plus tilde. So the universal cover of 2x2 real matrices with positive determinant. So this is kind of a natural space of stability conditions, this quotient, stab by GL2 plus tilde. And if you have any autoequivalence, it acts on this space. So in particular, the Serif Functor acts on this space. And what I'm saying is that there's no fixed point for that action. So there's no stability condition which, after you act by the Serif Functor, is itself modulo the action of GL2 plus. So the reason that that's maybe kind of interesting is that, for instance, for Fano threefolds, for a lot of the stability conditions that are known on Fano threefolds, they are known to be Serre invariant. Like, that's actually the crucial ingredient in the smoothness of moduli spaces for residual categories of cubic threefolds that I mentioned earlier. And so maybe there was some kind of hope that that could be true, more generally for Kuznetsov, for residual categories or Kuznetsov components. But yeah, it actually in general is not true. And it's just some general fact that when the Serre dimensions are not equal, then there can't be a fixed Serre invariant stability condition. Okay, so that was just something I wanted to mention quickly. And I think I have time. I think I have 7 minutes. So I think I'll mention a little bit about one last application of our theorem. So the last application is about the construction of singular fractional Calabi-Yau categories. Right, so what our theorem says is that these residual categories are usually not fractional Calabi-Yau, right? They're fractional Calabi-Yau up to the spherical twist. And the observation is that there's a way to make from that an honest fractional Calabi-Yau category at the expense of making it singular. So let me just write the result. So in the setting of the main theorem, okay, if you want, you can just think about the complete intersection and projective space case. And let me assume that X is smooth. Okay, if you noticed in the main theorem, I didn't assume X was smooth, but for this, let me assume X is smooth. Then there are two statements. So if you define this category, I'll call it Rx bar as the kernel of psi shriek. So that's a subcategory of Rx. So the statement is that this inclusion is a crepant categorical resolution of singularities. Okay, and so I'll just very briefly say what that means. So let me call, suggestively, I'm going to call this inclusion functor pi upper star, okay? So the fact that it's a categorical resolution is just the fact that you have a fully faithful functor from this category to this category, and this category here is smooth. This category here is smooth because X was smooth. And so that's like the definition of a categorical resolution of singularity. Singularity is a fully faithful functor into a smooth category. And crepancy is the following. So crepancy, so i.e., the right adjoint to this functor pi upper star, which I'll call pi lower star, is actually simultaneously its right and left adjoint, is also left adjoint. Okay, and I'm sweeping something under the rug here because technically speaking, this right adjoint pi lower star does not go from this category to this category. It really goes to something which you could call like the coherent completion of this category. So I'm sweeping something under the rug here, but like maybe I'll just say in words, for instance, what's the motivation for this definition? If you had a singular variety Y with rational singularities and you had a crepant resolution of it, then the pullback functor on perfect derived categories is a crepant resolution of categorical resolution of singularities. So that's the motivation for this terminology. It behaves like crepant resolutions of singularities of varieties. So that's the first part of the theorem. And then the second part is that this category, Rx, it's kind of like a Gorenstein variety in that it has a Serre functor. So this has, even though it's singular in general, it has a Serre functor. And it satisfies the following. So again, this is using the notation from the main theorem. That's what these numbers are coming from. So it's on the nose, it's fractional Calabi-Yau. There's no more spherical twist. So sort of passing to this kernel is a way to kill that spherical twist. So yeah, so I think that these categories could kind of be interesting because in general, fractional Calabi-Yau or Calabi-Yau categories have sort of the nicest properties. And maybe I can just mention one example, which I think shows that these categories are kind of interesting. Like a priori, this category, maybe I should note, is not an admissible category inside of D of a variety. It's just some subcategory of a variety. It's not necessarily a semi-orthogonal component. But the following example suggests that maybe you could hope for something like that in more general, in some kind of generality. So let's say that X is equal to M intersected with Y in P5. So this is a smooth 2-3 complete intersection. And so let me write and give equations, names to the equations for these varieties. So say M is the quadric, and Y is the cubic. Then it turns out that there's an interesting description of this category Rx. So what ends up happening is that there's an equivalence, of this category Rx bar. So this sort of crepant contraction category, which I just introduced, it turns out that it's actually equivalent to the residual category of Z, where Z is a certain cubic fivefold. So it's the following. Cubic fivefold. And this is singular, so it's a nodal cubic fivefold. Yeah, so what I'm saying is that in general, you can define this sort of crepant contraction, which I called Rx bar of Rx. That thing is genuinely fractional Calabi-Yau. A priori, it doesn't have any sort of geometricity. It's not an admissible subcategory anywhere. But at least in this example, it is admissible inside of a singular variety. In fact, it's the residual category of a nodal cubic fivefold. So I think it could be interesting to study these sort of crepant contractions more generally. But for now, that's all I have to say. So thanks. I think I'm out of time.
Great, thanks very much. Are there more questions?
So can I ask a question? So in this example, I mean this this non-existence of the Serre invariant stability condition. So does this give another direct proof that this Kuznetsov component for y1 and x6 are not equivalent?
Yeah, I guess maybe it does also give a proof of that. This form, I guess it does give a proof of that, just because one has a Serif Functor which is fractional Clobial and the other one doesn't.
Okay. Yeah, because Kuznetsov y1 it has a Serre invariant stability condition, right? But
that's maybe
yeah.
That's true. That's maybe a more difficult way to say it, but yeah. But even just from the form of the Serif Functors, I guess it implies.
Okay.
But they have different Hochschild homologies, so
that's another reason.
Okay. Okay.
That's another reason. Yeah. Numerically, they're sort of different. They're Hochschild homology.
So can you tell me what is the second Hochschild homology of the Kuznetsov component of this x6? What is the dimension of that?
I honestly forget.
Okay.
I don't remember. Someone else might know. Yeah.
Thanks.
You can. Yeah, I guess it's. You just need to compute H12. I don't remember off the top of my head.
actually for the residual category of x6, you just, I mean, the Hochschild cohomology of the entire d of x is just direct sum of all polyvector fields.
Mm-hmm.
And if you consider they are orthogonal to OX, which is Rx in this case, you just need to forget top polyvector fields. So you just forget lambda 3tx. And that's it.
Okay, thanks.
Can I ask a question as well?
Mm-hmm.
So, well, firstly, thank you for a very interesting talk. Secondly, in the context of the main theorem, which you haven't told us the proof of, but I'm quite curious about that. How do you know, or how do you establish that Serre functors on the residual categories exist in the first place? Because quite generally about spherical functors, we know that the twist and the co-twist, or well, what you call the twist of the target category and the twist of the source category, they intertwine left and right adjoints. And of course, left adjoint of a functor can be expressed as conjugation by Serre functors. So it seems to me that sort of this kind of formulas might sort of give the result that you ultimately claim, provided you know that the Serre functors on the residual categories exist and that the spherical functor restricts to a spherical functor on residual categories. I can sort of imagine what happens with showing that, the spherical functor restricts the spherical functor, but I'm curious, is there any general reason why the residual categories do have Serre functors?
Yeah, okay, there's a general statement. Suppose that you have a category with a Serre functor, and suppose you have an admissible subcategory. Then you can show that admissible subcategory automatically is a Serre functor.
That's true. And out of sheer interest, just could you say a few words about how do you prove the formulas for the Serre functors residual categories in terms of the spherical twists?
Okay, I don't think that I can say anything that would be succinct and satisfying, but the idea is, it really comes down to studying these things called rotation functors, which arise because, I guess I'm just repeating what I said before, that the Serre functor of this is given by the Serre functor of this category, composed with left mutation through here. And by some manipulations, you can write that as some autoequivalence composed with the following thing to some power. So the following thing is what I call the rotation functor, which is you tensor by O of 1. And then you left mutate back through here, and that gives an autoequivalence. And you need to prove a formula for some power of this functor. Yeah, I don't think I can say anything that's going to be super satisfying. I don't know.
I see. And the spherical functor you get, to which I upper star restricts on the residual categories, is that sort of fully faithful or conservative? I mean, is there anything we know about it?
Yeah. Well, I mean, at least I think very often it will be conservative, and that's what I was mentioning somewhere.
Yeah. I saw that, which is why I'm asking. Interesting.
Yeah. So at least I think that will be true in most examples. I mean, I don't know. You can't. maybe you could say that if maybe you could say, I said there was this more general categorical version of the theorem, and probably there is a way to put a condition on the spherical functor I pullback. In general, you replace I pullback with some arbitrary spherical functor. And there might be some condition you can put on that spherical functor to ensure its restriction is also conservative. But yeah, I think in essentially all the examples that you would cook up, this functor will be conservative.
Cool.
But yeah, we only checked it in this example here that I mentioned.
Thank you very much. And again, thank you for a very interesting talk.
Sure, thanks a lot.
And
Other questions?
Note, by the way, that spherical functors are never fully faithful.
Right, they're not, yeah.
Except from zero category.
Yeah.
Well, that's true.
Yeah. Conservative is a reasonable thing to ask for, yeah.
May I ask a question? First, a quick question. In the last example, is that this F2 and F3 are the same as the F2, F3 upstairs?
Sure. Yeah, they are. I just used the z's are the variables on the P6. Yeah, they're the same functions.
I see. Great. Okay. Yeah. Second question is that in the theorem for the upper dimension or lower dimension of Serre, the Serre dimension. So is there when you take this degree D to be like maximal and minimal, is there something special about this twist functor that then you can conclude that it does not contribute the dimension is estimated?
Can you say it one more time? If you take it, repeat one more time.
Oh yeah, I mean in this formula, there what is the special property of the twist functor when you take D to be like maximal or minimal?
Okay, I think that's an interesting question. I mean, if you follow, I didn't tell you the whole proof, right? But there are some inequalities that show up. Mm-hmm. And somehow the inequalities you can show are forced to be equalities if you choose the degrees in the right way. So it's a little bit, yeah, I don't know a great answer to that question. I think it would be interesting, for instance, to characterize in some intrinsic way the other degrees that appear. So this formula says something about the maximal and minimal ones, and the intermediate one should also capture some property of the Serre functor, and it might be in terms of like the entropy functor of the category. You can encode those numbers, but yeah, I don't know if I have a great answer for that. Besides, that's what works when you do the induction. When you really do the induction, you have to order these in the right way. So D1 is bigger than or equal to D2, bigger than or equal to DK, and if you order them that way, then everything works out, and these inequalities that come up all end up being equalities. So it sort of just falls out of the proof that you get the max and min. But yeah, I think it's an interesting question conceptually. What do the other degrees mean in terms of the Serre functor?
Yeah, also like just from the formula itself, it looks a little bit like in the survey condition, we take the maximum slope and minimal slope. So I wonder is that somehow the intermediate one.
I don't know if there's I don't know if there's any relation. Yeah.
Yeah. Okay, great. Thanks.
Sure. Mm-hmm.
Okay. Other questions? Well, if not, then there's, of course, as always, the